before we talk about sort of assessing the climate models and the forecast for warming in the coming centuries, we're going to sort of step back from that for a few weeks and talk about the carbon cycle, which is kind of the backstory, sort of the other story that we're talking about here. And on long time scales, the carbon cycle and the chemistry and climate of the Earth on sort of geologic time scales seems to have this sort of spooky stability. Like there's something going on. There's emergent behavior in the carbon cycle too that is it seems to be governing the way the Earth's climate evolves through geologic time, and this is the context, into which we're doing our what one writer, Roger Revelle, called grand geophysical experiment of putting a bunch of carbon into the atmosphere and seeing what happens. So the one expression of this kind of spooky stability of the climate system came from Carl Sagan, actually. And it's called the Fate-Young Sun paradox. So Sagan was an astronomer and a very successful sort of popularizer of science. He had some TV show, Cosmos, I guess, and everybody made fun of him for the way he said billions and billions of stars. But he spent a lot of his life reaching out to communicate science to people, but he also did a lot of really insightful and original scientific research. I mean, that's what he was primarily, as a scientist. And he came up with this paradox that stars like our sun, sort of generic, what they call main sequence stars, what most stars are, they get brighter as they age. And brighter, if you know about black body radiation, which is what the light coming from the sun is. It's just a black body curve, but it's so hot that it's sort of in the visible. Brighter means hotter, because the brightness is epsilon sigma t to the fourth, and so to get it brighter, you got to have a higher temperature. And actually, it's kind of cool. You guys have the sort of conceptual tools to understand why this is. A star is like a big cloud of gas, and there's weight, there's gravity that's pulling the gas together. And so if you think about at the center of the star, there's pressure inside that star, just like there is pressure here at the bottom of the atmosphere due to the weight of the atmosphere. Inside the star, the pressure is driven by the weight of the star, of all the gases in the star. So, the star will collapse until the gases in the center are at a high enough pressure that they can push back and hold the star, out from collapsing anymore. So what happens in a star, the fire that burns, that makes the heat, that makes the star, keep shining, is nuclear reactions, nuclear fusion. So it would be awesome if they could do nuclear fusion on Earth as an energy source. It's like this, holy grail in energy technology. They always say it's 40 years away. 40 years ago it was 40 years away, and now it's 40 years away. It's really hard to make a star on Earth in a controllable sort of way. But the way it works is that hydrogens combine in these nuclear reactions to make helium. And so and hydrogens are smaller than helium, so it takes 4 hydrogens to make a helium. So now the pressure has to be held as you make more of the helium. The pressure at the center has to be sort of borne by fewer atoms after you make more heliums out of the hydrogens. By fewer atoms, but they are heavier atoms. So, you might think that a heavy atom can hold up as much pressure as 4 light atoms could, but we already talked about how pressure, which is just the energy of things bouncing off of a wall. If you have a pressure gauge, like if you had a tire pressure gauge in the center of a star, what you're measuring is the force of the atoms bouncing off of the, some membrane there. And we already said that heavy atoms don't contribute more to the pressure than light atoms do, because light atoms at a given temperature are moving faster, right? So the ping pong balls and the bowling balls, you would think, you're throwing ping pong balls against the wall and bowling balls against the wall, you would think that the bowling balls would push harder, right? But if you're putting the same amount of energy in to the ping pong balls and the bowling balls, which is what the 1/2 kT energy, that's how much energy they have at whatever temperature, it's just a function of the temperature. It just works out that the ping pong balls are going faster enough that they contribute as much to the pressure as the bowling balls do. So we do this nucleosynthetic reaction, and we combine light atoms into slightly heavier ones. And so now, if the temperature was exactly the same before you do the reaction, you've got 4 times as much pressure as after you do the reaction, because it's just based on the number of atoms. It doesn't care how heavy they are. So if the temperature stayed constant, the pressure would drop by a factor of 4 when you make a helium out of 4 hydrogens. But the pressure has to balance the weight of all this stuff, and the amount of mass in the star hasn't changed very much, basically not at all. And so you can't have 1/4 of the pressure and still have the star, holding itself up. So what happens is the pressure has to balance the star's mass, and so the temperature has to go up. So 4 of those guys are holding up the star, and they can do that at a slightly cooler temperature. But when one atom has to hold it up all by itself, it has to be 4 times the pressure per atom. It has to be moving faster. So by swapping 4 ping pong balls for 1 bowling ball, we've lost some of our push power if the temperatures are the same. So you have to throw the bowling ball harder to get it to hold the star up. So the bottom line is that as you convert the hydrogen to helium, the temperature on the inside of that star has to go up just to hold the star out, to hold it up, to balance the weight of the gases in that star. So this is something that's been known for a long time to astrophysicists and astronomers like Carl Sagan. But what Sagan did was to think about what this means to the Earth. So when the Earth was new, some 4 billion years ago, the solar constant, which we've been calling L, was 25% lower. The sun was cooler. It's hotter today than it used to be. So if you were to take a climate model and fix it up so that it gives you the right temperature for the Earth today, given how hot the sun is today, and then just abruptly dial the sun down 25%, the Earth would freeze. Or if you set up a planet that was, at some reasonable sort of temperature where you can have liquid water in early Earth history, and there are sedimentary rocks that go back all through Earth history, and then you dial up the sun by 25%, it would have a runaway greenhouse effect. So somehow the energy source for the planet has been getting hotter over geologic time, and yet the temperature of the Earth has stayed within fairly narrow temperature bands of about the melting point of water. In a liquid water phase. It never had a runaway greenhouse effect, so we never boiled the oceans dry, because if you did that, you'd never get it back. And it never froze for very long anyway. So this is the faint young sun paradox. How is it that the Earth is so stable even though the energy source is changing with time? There's another example of spooky stability in the Earth system, which has to do with atmospheric oxygen. Which it comes from plants doing photosynthesis, is where the oxygen in the atmosphere comes from. And we'll talk more about this when we start talking about fossil fuels, because the plants grow, they release oxygen, they make fossil fuels, and sort of we burn the oxygen and the plant material in the presence of oxygen to get the energy back out. So the Earth, the atmosphere has had oxygen for something like 500 million years. Has had oxygen levels something like what we have today. Probably there was a little bit of oxygen going much further back into Earth history, but for at least the last 500 million years or so, there has been enough oxygen to keep critters alive like us. So there are bacteria that can live perfectly happily with no oxygen. The first earliest forms of bacteria evolved when there was no oxygen, and so that's how they are happy. But multicellular critters like us, we have to have pretty high levels of oxygen in the atmosphere. So if O2 dropped by a factor of 10, if instead of 20% of the atmosphere it was only 2% of the atmosphere, then that's it for us. We all kind of gasp and fall down and die, and that's that. And we know that from fossils there have been multicellular animals throughout this 500 million years of Earth history, and they never asphyxiated. Alternatively, if the oxygen concentration was 10 times higher than it is today, one spark and you'd get a forest fire that would wipe out an entire continent. At some point you get enough oxygen and wet wood will burn. So once you start a fire, there's nothing that would stop it in that case. So there's no obvious a priori reason why atmospheric oxygen should have risen right up to this level, which is just perfect for us, and stayed there for this long a period of time. It's not obvious why that is. So the Earth's climate seems to be kind of stable in this spooky sort of way. and also the oxygen concentration in the atmosphere seems to be stable in this spooky sort of a way. And one explanation for this, well, or statement of the problem anyway, comes from this British geochemist named Lovelock, who came up with an idea called the Gaia Hypothesis. And one title of a paper that they submitted at the time, this is sort of back in the 70s, although Lovelock is still writing books which are very fun and colorful to read. But one sort of succinct statement of this that they used as a title of a paper was homeostasis, which means self-regulating behavior. So we have homeostasis to regulate our internal body temperature, for example. Homeostasis by and for the biosphere. So they're imagining all of life on Earth as being like this huge, integrated, functioning superorganism that regulates the CO2 and the oxygen and other things about the Earth for its own advantage. You know, the same way that we regulate our body chemistry and our body temperature in order to survive. This idea is that the whole planet kind of does that. And it's a very intriguing idea. His first big book was published in 1976. I started graduate school in 1980, and you know, the romantic appeal of this idea was part of my, oh, this sounds really cool. I think I'll throw my life away studying that instead of, you know, whatever else I might have had in my head at that time. But it's a hard, in some sense, it's almost not really a testable, it's like a philosophy rather than sort of a testable, I mean, how do you test something like this? There's also the problem of how we think that evolution works. Evolution is sort of a process of trial and error. You have random mutations, and most of them, you know, don't do very well. But the ones that do propagate their genes to the next generation, and so you have natural selection. And this happens on the level of individuals or species or something like that. Whereas if you're talking about the whole planet is one big organism, there's no room for screwing up. There's no room for trial and error. You don't have a million Earths, and then you just take the ones that sort of function and then let those, you know, fill up the rest of the Earths with their genes. It sort of doesn't jibe with how we think evolution works. And plus there's also this issue of altruism, which is, you know, Gaia would say that the function of some organism might be to produce methane, for example. And the methane then has some use in the big Gaia machine, and so these bacteria make methane, which then, you know, benefits everybody. But what if there were cheater bacteria that derive all the benefits from, you know, the other bacteria doing their altruistic jobs to keep Gaia going, but this particular organism doesn't want to do that, you know, he's selfish, and so they're going to cheat. And you know, how is it that this thing could sort of be stable? It's just a funny, you know, there's no answers, yes or no, about Gaia, but it's just a very interesting, intriguing philosophical idea that the Earth biota could somehow be working together in these sorts of ways. So there is actually an explanation, though, for the stability of the climate of the Earth. The faint young sun paradox. We can make Carl Sagan happy without invoking any mysticism. No Gaia. We don't need Gaia to keep Carl Sagan happy. So I'm going to show you sort of a theory for how the carbon cycle works in geologic time that can explain why the Earth's climate is so stable over its long history. So you could say that science really gets interesting when you start reading these pop books that kind of go the next step into sort of mysticism. And quantum mechanics did that by, this duality and the Tao of physics and all of that. And now the Earth science we've got our Gaian people too. So it's kind of cool. I mean, whether you buy it or not. Anyway, the carbon cycle of the Earth. The way to visualize it at the first glance is to have the atmosphere kind of as the center of the action. And then you have various other components of the carbon cycle which all interact through the atmosphere. So you have the land surface, the trees and the soils and things, and that releases carbon to the atmosphere and takes it up from the atmosphere. And you have the ocean, which has a lot more carbon in it actually than the atmosphere does. It's kind of a heavy hitter in this thing, which exchanges carbon with the atmosphere. And then you have the solid Earth, which does the same thing. So we're going to talk about all three of these components and sort of how they work as we think about the carbon cycle and how it works, what the backstory is, and how it will respond to taking a bunch of carbon out of the solid Earth, which is fossil fuels, and putting it into the atmosphere, and how it might, interplay with these other things. We're sort of going to go through this in the next this lecture and then the next one. But for today, we're looking at just this part of the carbon cycle, the interaction with the solid Earth. And the behavior, what we're talking about, the basic picture, all boils down to one chemical reaction, which is called the Urea reaction. Harold Urey mentioned this on page 57 of a book that he wrote when he was actually here at the University of Chicago, and he, it's since sort of been named after him. He wasn't the first to figure this out, but a name is a name. So the reaction is like this. Starts with this thing: calcium, silica, and then 3 oxygens. This is the simplest possible formula that you could write for an igneous rock. So igneous means that it was melted. It was lava or magma, and then it froze. And so, crystalline rocks, granite, if you have a granite countertop, that's an igneous rock. Basalts are rocks that form in the ocean sediment, in the crust of the ocean. They form from lava. And they have chemical forms that are sort of like this. They have other elements in them. They have sodium and iron and things like that. So it's more complicated than this. A real geologist wouldn't look at this and say that's a rock. But it captures the essentials as far as we need. So that's the first ingredient. The next is CO2 gas. So that's one side of this chemical reaction. And we're going to write double arrows. Which are going to mean that this chemical reaction, the two sides are in equilibrium with each other. And we're going to learn more about what that means. That has very special meaning, equilibrium. It means that there is some distribution of the chemicals, some amount of this and some amount of this and some amount of the ones on the other side, which will be the lowest energy. And And then once you start with an equilibrium, you can sort of perturb it and poke it, and it does things that we will, be using, especially when we talk about the chemistry of the oceans. Anyway, so that's on one side of the reaction is this igneous rock and CO2 gas. On the other side, we have calcium carbonate, which is limestone. And SiO2, which is well, glass is mostly made out of SiO2. It turns out that both of these kinds of material, calcium carbonate and this SiO2, are sedimentary rocks. So calcium carbonate and silica are two of the main things that you find in sediments of the ocean. So we got igneous rocks on one side and CO2 gas, and then sedimentary rocks on the other side. So one thing that can change the equilibrium of a reaction like this, I mean, where, if it wants to have most of the stuff be in this form or in this form, is the temperature. It turns out that if the temperature is really high, it tries to make, it wants, the lowest energy state is to have everything be in this form. And at sort of room temperature, like at the surface of the Earth, things want to be in this form. Now, it sort of makes sense because, all of these are solid and crystalline, or, very ordered, except for the CO2 gas, which is a gas. And so just like we talked about water, that it can be in the liquid state, which is kind of all bound up and constrained, versus the gas. If you put more heat energy in and the water molecules are starting to get agitated, they want to be in the gas phase because they're sort of less constrained there. And the same is sort of true here, that if you take some calcium carbonate and silica and you heat them up, the carbon that's in there gets kind of agitated by the high temperatures, and it wants to be in the gas. It wants to be free. It wants to be unconstrained. And so that's why this side of the reaction is where things go if you heat it up, whereas this side is where it goes at sort of room temperature. So high temperature, where you find high temperature is in the deep earth, and low room temperature you find at the surface. So the surface wants the carbon to be in this form of calcium carbonate. So the equilibrium, if the surface got its say, the lowest energy state at the surface would want the partial pressure of CO2, the amount of CO2 in the air, to be only about 10 parts per million. So the real atmosphere has 385 parts per million CO2 in the air. And that's higher than natural because of fossil fuel combustion, but according to the ice cores, before the industrial age started, there was 280 parts per million in the atmosphere. So the natural atmosphere equals 280 parts per million. And so the natural atmosphere had 28 times more CO2 in it than the equilibrium, according to the surface of the Earth, would want. So theoretically, if you took some room temperature calcium carbonate rocks and some air, and you let them find their lowest energy state, it would suck the CO2 right out of the air until it was down at like 10 parts per million. Now the deep Earth, on the other hand, is hot enough, and it makes this reaction, it makes the CO2 want to be free as a gas. So in the deep Earth, CO2 goes to the gas form, and if the deep Earth had its way, all of the carbon goes to the gas form, and we would end up with Venus. Venus has 70 atmospheres of CO2 in the air. So Venus and Earth both kind of got the same. We got the same amount of carbon to start with, it's thought. And you know, the Earth mostly has its carbon in the form of calcium carbonate, whereas Venus, it's all in the atmosphere. It's all gotten cooked, and it's out in the atmosphere now. And so if there were more carbon on Venus, you'd have more carbon in the atmosphere. But as it is, it just goes until it sort of runs out of carbon. So there's this tug of war. The surface wants the CO2 concentration to be low, and the deep Earth wants it to be high. It wants all of Earth's carbon to go into the atmosphere like Venus. There's this pushing against each other. So it turns out that this competition, you know, this pushing against each other between the hot interior and the cold exterior of the planet creates a thermostat. It creates a negative feedback system, which we'll call the CO2 thermostat. So we can kind of put this into the context of a sort of a schematic Earth. This is a volcano. And there's CO2 coming out of the volcano from the Earth to sort of start with. Actually, more than half of the CO2 coming out of the Earth is coming out of hot springs in the deep ocean rather than into the atmosphere, but that doesn't really matter all that much to our story. And actually, also just totally, a trivia question that's kind of intriguing. Some astonishingly large fraction of the CO2 coming out of the Earth apparently is coming out of Mount Etna in Sicily, or wherever Mount Etna is. I think it's in Sicily. It just happens that there's some carbonate rocks down there that are getting cooked, and the CO2 is escaping. So just the luck of the draw, it just turns out that there's a lot of CO2 coming out there. But where it comes from doesn't really matter. We have CO2 coming out of the Earth and going to the atmosphere. So that's sort of one step in this cycle. Now the CO2 in the air is combining with igneous rocks, and it's ultimately making sedimentary rocks, which wind up on the floor of the ocean. So let me write the reaction again. The reaction going in this direction from the igneous rocks to the sedimentary rocks, that direction has a name. It's called weathering. So you're making these calcium carbonate rocks, and they deposit on the seafloor, and then the plates on the seafloor that the sediment is accumulating on, they get subducted. So the plates form at these spreading centers, and then they spread out, and eventually they get dense enough that they sort of sink back down into the earth. That's sort of plate tectonics. And when they do, they carry some of the sediment that has accumulated on them down into the earth. So the carbon now in the calcium carbonate has been carried down into the deep earth, and it's hot down there. So when it's hot, this equilibrium reaction tends to get pushed in this direction, and there's a name for this also, metamorphism. Is the name of the chemical reaction going that way. So there's subduction and metamorphism that happens there, and when you make new igneous rocks out of the old sediments and the CO2 is then going to want to escape, and so it sort of completes this loop, this whole loop of carbon going from the atmosphere down to the earth in the form of calcium carbonate, and then being metamorphosed by getting cooked and releasing the CO2 back to the atmosphere again from the solid earth. So, you know, in the carbon cycle that I drew, the atmosphere and the solid earth, here's coming out and there's kind of going in. So the volcanoes, they don't care about climate. The rate of CO2 going to the atmosphere depends on lots of things, like, you know, how much plates are being subducted and whether they have calcium carbonate in them or not, and whether some, you know, deposits of calcium carbonate just happen to get hit by a bunch of hot magma like is happening at Mount Etna. You know, there's variations presumably in how much CO2 is coming out of the Earth, but they don't care about the climate at all. So this is sort of a driver. To this carbon cycle. The rate of weathering in contrast cares very much about the climate of the Earth. So weathering, you got to dissolve rock plus CO2 into water. And then the water carries the dissolved rock down to the ocean, where it gets turned into calcium carbonate and silica by critters, mostly by plankton that make shells out of calcium carbonate and silica. But if you don't have the water to carry the rock, then you don't do this chemical reaction. The reaction requires water. There's a place in Antarctica called the Antarctic Dry Valleys, and there's never any rainfall there. And so the surfaces of the rocks there are millions of years old. They're not dissolving away the way they do every place else. Now, how much water you have to sort of flush over the rocks to dissolve them and do this weathering reaction depends on the temperature. So if you have a lush tropical world, there's more rainfall and more water sort of flushing over the rocks dissolve them and carry them away and do this weathering reaction than if you had a very cold planet that didn't have much water. In a cold world, there wouldn't be as much water flushing over the rocks to do this chemical reaction. And of course, the temperature depends on CO2. Let's see, I don't want to erase my cartoon there, so I'm going to... So we end up with a stable negative feedback if the CO2 was too high. There'd be lots of weathering, and there'd be more weathering than the CO2 coming out of the Earth. And so you're taking more out than you're putting in, and so that means that the CO2 concentration drops. So if it's too high, it goes down. That's a negative feedback. It's stabilizing the CO2. If it's too low, there's not enough weathering. So now you got more coming in from volcanoes than you're taking out by weathering. And so the CO2 concentration will tend to rise up. So if we had a time plot of the CO2 concentration in the air, there could be some value at which weathering equals degassing. That would be the stable point. And if we were higher than that, it would tend to get pulled down to that value. Or if you started out with not enough CO2, it would tend to rise up to that value. So that can explain, at least in part, Carl Sagan's paradox that the sun can get brighter through geologic time, and the Earth's climate has this thermostat that keeps the temperature at about the right level so that there's enough liquid water to do this chemical reaction to balance the carbon cycle.